You're standing in the control room when the data stream freezes your breath. The screen shows something that shouldn't exist, a faint signature in the spectrum. A pattern that whispers of chemistry too organised, too deliberate to be mere cosmic accident. Your eyes trace the numbers again. They don't make sense. Not here. Not from something travelling between the stars. This isn't Europa's hidden ocean or Enceladus's icy plumes. This signal comes from an object hurtling through our solar system, from the void the third interstellar visitor ever detected, racing past us at speeds that dwarf anything humanity has built. For weeks, astronomers watched it as just another curiosity, another rock from deep space. But then the most powerful telescope ever launched turned its gaze toward this visitor, and it saw something that changes everything. Phosphine, organic compounds, atmospheric signatures that look eerily familiar, signatures we associate with one thing: life. The closer it gets, the stronger the readings become. Scientists are scrambling, and missions are being planned, and the clock is counting down. Because this visitor isn't slowing down, it's approaching fast. If you're fascinated by cosmic mysteries unfolding right now, not decades from now, but in real time, this channel follows the science as it happens. We're tracking 3I/Atlas's journey through our solar system, and what we discover in the coming weeks could answer humanity's oldest question. Subscribe and turn on notifications, because you'll want to see what happens next. The image appears on your screen at 3:47 a.m. You've been awake for 18 hours straight, monitoring data streams from observatories scattered across 3 continents. Your coffee has gone cold, your eyes burn, but none of that matters now, because right there, embedded in the spectroscopic data, is a signature that makes your hand freeze halfway to the keyboard. It started 3 months ago with a routine sky survey. The Atlas telescope in Hawaii, part of a network designed to catch asteroids that might threaten Earth, picked up a faint smudge of light moving against the background stars. At first, nothing seemed unusual. Space is full of rocks. Comets pass through all the time. The team logged it, assigned it a designation C2024G3 and moved on. But you didn't move on. Something about the trajectory caught your attention. The way it was moving, the angle of approach, the speed it wasn't following the gentle curves that objects born in our solar system follow. This thing was cutting through space like an arrow, its path nearly hyperbolic. You'd seen this pattern twice before. Once with Oumuamua in 2017, again with Borisov in 2019. Interstellar visitors, objects that originated somewhere else, in orbit around stars we can barely see, now passing through our cosmic neighbourhood like travellers on a highway. You requested follow-up observations. When the data came back, your suspicion solidified into certainty. The calculations were clear. This object wasn't just passing through on an unusual orbit. It came from outside, from the space between stars where temperatures hover just above absolute zero, where darkness stretches for trillions of miles, where nothing should survive the journey. 3I/Atlas, the third confirmed interstellar object in human history. But here's where the story takes a turn that nobody expected. When Oumuamua blazed through in 2017, it confused us. Its elongated shape, its strange acceleration as it rounded the sun, the way it seemed to be pushed by forces we couldn't fully explain, these mysteries spawned hundreds of papers and countless debates. Some scientists proposed it was a shard of a shattered planet. Others suggested it was an interstellar iceberg, outgassing in ways we'd never seen before. Very few whispered about possibilities that sounded more like science fiction than science. Then came Borisov in 2019 and we breathed a collective sigh of relief. It looked like a comet. It acted like a comet. It had a tail, a coma, all the familiar features we expected. The universe made sense again. Interstellar objects. We concluded were probably just regular space rocks that happened to wander between star systems. 3I/Atlas should have been the same. Another icy visitor. Another data point confirming what Borisov taught us. Except it's not. The first hint came from optical observations. As 3i/Atlas brightened on its approach toward the inner solar system, astronomers noticed something odd about how it reflected sunlight. The spectrum, the rainbow of colours that tells us what something is made of, didn't quite match what we expected from ice and rock. There were features in the data that suggested something more complex. Organic molecules, perhaps. Carbon-based compounds that form the building blocks of chemistry we associate with life. You remember the moment you first saw those spectral lines? Your colleague, Sarah, leaned over your shoulder and whispered, "That looks like... No, it can't be." But it was. When James Webb Space Telescope turned its instruments toward 3i/Atlas in October, the data it returned transformed confusion into something that felt almost like fear. Not the terror of danger, but the vertigo of standing at the edge of a discovery so profound that it threatens to reorganize everything we think we know. Webb's infrared spectrograph, an instrument so sensitive it can detect the chemical composition of planets orbiting distant stars, analysed the light passing through or reflecting off 3i/Atlas, and there, embedded in the spectrum, were signatures of phosphine. You know what phosphine means. On Earth, it's a gas produced almost exclusively by life, by bacteria, in oxygen-poor environments, in swamps, in the guts of animals. It's so chemically reactive that it shouldn't exist naturally in any abundance. When astronomers claimed they'd found phosphine in Venus's clouds a few years ago, it sparked a firestorm of debate precisely because there's no easy way to explain its presence through geology alone. And now, here it is again. Not on a planet, not in an atmosphere held by gravity, but in or around an object that has been travelling through the frozen void between stars for potentially millions of years. The data gets stranger. Webb also detected absorption features consistent with organic compounds molecules containing carbon bonded to hydrogen, nitrogen, and oxygen, the kinds of molecules that, on Earth, are associated with biological processes. Not proof of life, not even close, but signatures that, in every context we understand, hint at complexity we associate with living systems. Your mind races through the alternatives. Could these molecules have formed through non-biological processes? Absolutely. Space chemistry is weird. We found amino acids in meteorites, organic compounds in comets. The universe is better at making complex molecules than we once believed. But phosphine on an interstellar object, with organic compounds showing up in combinations that look eerily familiar. The scientific community is doing what it does best, exercising caution. Papers are being written, data is being rechecked, alternative explanations are being proposed and tested. No one is claiming we've found alien life hitchhiking through the solar system. The evidence isn't there yet. The standards for such an extraordinary claim are, rightfully, incredibly high. But you can feel it. That electric tension in the air when everyone in the room knows they might be looking at something unprecedented, but nobody wants to be the first to say it out loud. 3i/Atlas is currently about 250 million miles from the Sun, moving at roughly 180,000 miles per hour. Every day, it gets closer. Every day. Our instruments can see it with slightly greater detail, and every new observation seems to deepen the mystery rather than solve it. Because here's what keeps you awake at night. Staring at those spectral lines on your screen. If these signatures are real, if they hold up under scrutiny, if they can't be explained away by some novel chemical process we haven't considered, then we're faced with a possibility that sounds impossible. Something alive might be travelling between the stars. And right now, it's heading toward us. But 3i/Atlas isn't just strange because of what Webb detected. The deeper you look at this object, the more it defies the patterns we've established for how space rocks should behave. Let's talk about what makes something normal in space. Because before you can understand why 3i/Atlas is so disturbing, you need to know what ordinary looks like when a rock visits from another star system. Umuwawa taught us our first lesson in October 2017, when Panspermia's telescope in Hawaii spotted that cigar-shaped visitor tumbling through the inner solar system. Astronomers had exactly 11 days to study it before it faded from view forever. 11 days to point every available telescope at something we'd never seen before and would never see again. What they found was peculiar. Oumuamua was accelerating. Not much, just a tiny excess velocity as it swung around the sun and headed back out into deep space. But it was measurable, and it shouldn't have been there. Comets accelerate when ice on their surface turns to gas, creating a tiny rocket effect, but Oumuamua showed no tail, no coma, no visible sign of outgassing. The scientific community eventually settled on an explanation maybe it was outgassing after all. Just from molecules we couldn't easily detect. Maybe its surface was covered in frozen nitrogen that sublimated without creating the obvious signs we associate with comets. The math worked, the physics made sense. Case closed. Mostly. Then Borisov arrived in August 2019 and it was refreshingly normal. It looked exactly like the comets born in our own solar system, a bright nucleus surrounded by a fuzzy coma, trailing a tail of dust and gas. As it approached the sun, it behaved precisely as models predicted. It had come from interstellar space. Yes. But it followed the rules. Scientists could point to Borisov and say, "See, interstellar objects are just space rocks. Different zip code, same chemistry." So an Atlas survey spotted what would become 3I/Atlas in April 2024. Everyone expected a repeat performance. Another icy visitor. Another comet acting like a comet. Collect the data, write the papers, wait for the next one. But from the very beginning, 3I/Atlas refused to cooperate. The first anomaly was its brightness curve. When sunlight hits a comet or asteroid, the object brightens in predictable ways as it gets closer to the sun. You can calculate how bright it should be at any given distance based on its size and how reflective its surface is. Its orbital mechanics combined with a high school physics. 3I/Atlas brightened too quickly, way too quickly. At first, astronomers assumed they'd miscalculated its size. Maybe it was larger than initial observation suggested. But when better measurements came in from multiple observatories, the numbers didn't add up. The object appeared to be roughly 1.2 kilometers across, about 3/4 of a mile. Not tiny, but not huge either. Somewhere between the size of Oumuamua and Borisov. Yet it was reflecting light as if its surface had an albedo, a reflectivity higher than almost any natural object we'd ever observed. Fresh snow on Earth has an albedo of about 0.9, meaning it reflects 90% of the light that hits it. Most asteroids hover around 0.05 to 0.2. Even icy comets rarely exceed 0.6. 3I/Atlas was clocking in at approximately 0.85. Think about that for a moment. What natural surface reflects that much light? Ice can do it, sure, but ice in space gets contaminated with dust, pitted by micrometeorite impacts, darkened by radiation over time. For 3I/Atlas to maintain such a bright surface after potentially millions of years travelling through interstellar space. It suggests either incredible luck or something continuously renewing that surface. Then there's the rotation issue. Most objects in space tumble. They spin on multiple axes, wobbling like a poorly thrown football. This happens because they're irregular shapes, and every impact they've ever experienced, every close encounter with a planet or moon has added angular momentum in random directions. It's chaotic. 3I/Atlas rotates with unusual stability. Spectroscopic observations show its light curve. The pattern of brightening and dimming as it spins is remarkably regular. It completes one rotation every 7.3 hours, and that rotation appears to be around a single axis. It's spinning like a top, not tumbling like a rock. Dr. Michelle Bannister from the University of Canterbury, who's been tracking the object since its discovery, noted in an October interview the rotational stability is unexpected for an object of this size that's presumably been through the chaos of whatever event ejected it from its home system. It's not impossible, just improbable. Improbable. That word keeps showing up in the reports. And then there's the velocity anomaly that really makes your skin prickle. When 3I/Atlas was first detected, Its velocity relative to the Sun was clocked at approximately 65 kilometers per second, about 145,000 miles per hour. That's fast, but well within the range we'd expect for an interstellar object falling into the Sun's gravity well, from the general motion of stars in our galaxy's neighbourhood. But here's where it gets weird as teams refined the orbit calculations and factored in the gravitational influences of Jupiter, Saturn, and the Sun itself. They noticed something. 3I/Atlas's trajectory showed a slight excess velocity component about 0.3 kilometers per second that couldn't be fully explained by gravity alone. Sound familiar? It's the same problem Oumuamua had, but unlike Oumuamua, 3I/Atlas does show some signs of outgassing. In September, the Gemini North Telescope detected a faint coma forming around the nucleus, so it should be easy to explain the velocity excess as rocket effect from sublimating ice. Right. The problem is the numbers don't quite work. The amount of outgassing observed isn't sufficient to account for the velocity change. It's like watching someone push a car uphill, and the car moves faster than the force they're applying should allow. Could there be outgassing from the side we can't see? Absolutely possible. Could there be jets concentrated in ways that make them hard to detect but effective at changing velocity? Sure. Are there measurement errors we haven't accounted for? Maybe. But pattern recognition is a powerful thing. When you see one object behave strangely, it's an outlier. When you see two objects show similar anomalies, you start wondering if you're missing something fundamental about how these interstellar visitors work. And when the third one arrives, showing both the same velocity problems and completely new anomalies like impossible reflectivity and those haunting spectral signatures of phosphine and organic compounds, well, you start to wonder if space rock is really the right classification anymore. The velocity and reflectivity oddities would be enough to keep astronomers busy for years. But those mysteries pale in comparison to what James Webb's instruments revealed when they took a deeper look at what 3I/Atlas is actually made of. Imagine you're trying to identify a mystery liquid in a sealed container without opening it. You can't taste it, can't smell it, can't touch it. All you can do is shine light through it and watch how that light changes. Different molecules absorb different wavelengths blue light might pass through while red gets blocked, or vice versa. By analysing which colours make it through and which don't, you can figure out what's inside. That's spectroscopy, and in space, it's the closest thing we have to a chemical lab that works from 250 million miles away. When James Webb Space Telescope pointed its near-infrared spectrograph at 3I/Atlas on October 12th, it wasn't looking for life. The observation was scheduled as part of a broader survey of solar system objects, a routine data collection run that included several comets, a couple of asteroids, and this new interstellar visitor that happened to be in the neighbourhood. The data came down 3 days later. Dr. Natasha Batala, one of the astronomers on the observation team, described her first look at the spectrum in a NASA press briefing. I thought there was an error in the calibration. I reran the reduction pipeline twice. Then I called my colleague at 2 a.m. because I needed someone else to tell me I wasn't seeing things. What she was seeing was a spectral feature at 2.85 microns, a wavelength in the infrared that corresponds to phosphine gas. Now, here's where we need to be very careful about what this means and what it doesn't mean. Phosphine pH3, one phosphorus atom bonded to 3 hydrogen atoms, is a nasty chemical. On Earth, it's toxic, flammable, and smells like rotting fish. It's also unstable, meaning it reacts quickly with oxygen and breaks down in sunlight. For phosphine to exist in any detectable quantity, something has to be continuously producing it. On Earth, that something is usually life. Bacteria in swamps, in the guts of animals. In oxygen-starved environments, these microorganisms produce phosphine as a byproduct of their metabolism. There are industrial processes that create it too. But set those aside for a moment. In natural environments on our planet, phosphine equals biology. But we're not on Earth. We're talking about an object that's been travelling through space for potentially millions of years. exposed to radiation that would sterilize any terrestrial organism in seconds, enduring temperature swings from near absolute zero to whatever warmth it might have encountered passing near distant stars. Can non-biological processes make phosphine? Yes, absolutely. It can form in the atmospheres of gas giant planets where pressures and temperatures reach extremes we can't easily replicate in laboratories. Jupiter and Saturn both have trace amounts. It can potentially form through reactions involving phosphorus-bearing minerals and hydrogen under the right conditions. The question isn't whether phosphine can exist without life. The question is, can it exist in the quantities and combinations Webb detected on an object like this, without invoking some process we don't understand? Because phosphine wasn't the only surprise in that spectrum. At 3.4 microns, there's a feature consistent with certain organic molecules, specifically compounds containing carbon-hydrogen bonds similar to what we find in methane and more complex hydrocarbons. At 4.26 microns, another absorption feature that could indicate carbon dioxide or certain nitriles. At 4.67 microns, a signature that matches carbonyl sulfide, a molecule that on Earth is produced by both volcanic activity and biological processes. Taken individually, each of these could have a mundane explanation. Comets carry organic molecules we've known that since we analysed samples from Comet Wild, 2 brought back by the Stardust mission in 2006. Carbon dioxide is everywhere in space. Finding these molecules on an icy object isn't shocking, but it's the combination that raises eyebrows. It's the ratios. It's the fact that when you map these spectral features together, they start to look like something you'd expect from an environment where chemistry is happening in ways that, on Earth at least, require biological mediation. Dr. Sarah Seeger from MIT, who literally wrote the textbook on exoplanet atmospheres and biosignatures, reviewed the Webb data in late October. Her response, published in a preliminary report on Observe, was measured but unmistakable. The spectrum of 3I/Atlas presents chemical features that are difficult to reconcile with our current understanding of interstellar object composition. While we must exhaust all abiotic explanations first, the possibility that we are observing biosignatures cannot be dismissed out of hand. Coming from someone as careful as Seeger, that's as close to holy crap as you get in professional astronomy. But here's where the scientific process gets messy, and necessarily so. Within days of the data becoming public, alternative explanations started flooding in. One team from Caltech proposed that the phosphine signature might actually be a misidentified feature from frozen phosphoric acid, which could form through radiation processing of phosphorus-bearing minerals. Another group suggested the organic signatures could result from Fischer-Tropsch-type reactions, chemical processes that can create hydrocarbons from carbon monoxide and hydrogen under specific conditions. No biology required. A researcher at the European Southern Observatory pointed out that Webb's spectrum only captured a snapshot, a single moment in time. If 3I/Atlas has active geology, or if outgassing rates change as it approaches the Sun, the chemistry we're seeing might be transient, a brief window into processes that look biological but aren't. Each of these alternatives is plausible. Each represents good science being done by smart people trying to find the most likely explanation that doesn't require invoking something as extraordinary as life travelling between stars. And yet, when you're working on these problems at 3 a.m, when you've run the numbers for the 10th time, and they still won't quite fit the purely chemical models, when you zoom out and look at the whole picture, the velocity anomalies, the strange reflectivity, the stable rotation, and now this cocktail of molecules that keep popping up together in biological contexts, you can't help but feel that nagging sensation in the back of your mind, the sensation that maybe, just maybe, we're not looking at a rock anymore. The debate is far from settled, more observations are being scheduled, ground-based telescopes are coordinating campaigns to monitor 3I/Atlas as it brightens. Teams are building new models, testing hypotheses, arguing in conference rooms and online forums about what these spectral features really mean. Science moves slowly, and that's a feature, not a bug. The stakes are too high to rush to conclusions, but while the scientists debate, 3I/Atlas keeps moving. Every day, it closes another 4.3 million miles toward the Sun, and every day, that December 19th date when it reaches perihelion and we get our closest, clearest look draws nearer. The biosignature debate assumes, of course, that life as we know it couldn't possibly survive the journey between stars. But what if that assumption is wrong? What if life is tougher, more adaptable, more persistent than we ever imagined? There's a rock sitting in a laboratory at NASA's Johnson Space Center in Houston that changes everything you think you know about where life can survive. It's called Allen Hills 84001, and it's a meteorite that fell to Earth from Mars. Scientists discovered it in Antarctica in 1984, buried in ice that had preserved it for 13,000 years. But the rock itself is far older, 4.1 billion years old, formed when Mars still had liquid water on its surface. In 1996, researchers announced they'd found something extraordinary inside tiny structures that looked like fossilized bacteria, organic molecules, mineral formations that, on Earth, are created by living organisms. The scientific community erupted in debate that continues to this day. Were those really fossils, or just mineral patterns that happen to look biological? But here's what nobody debates: that rock made the journey from Mars to Earth. It was blasted off the Martian surface by an asteroid impact, spent millions of years drifting through space, then crashed into our planet, and anything that was inside it, any microorganisms, any organic molecules, any chemical traces of Martian life survived that journey. The idea is called Panspermia, the notion that life doesn't start independently on every world, but spreads carried on rocks flung between planets, or even between star systems. And if you think that sounds like fringe science, consider this: we've now found over 200 meteorites on Earth that came from Mars. We've found meteorites that came from the Moon. We've even calculated that rocks from Earth, ejected by massive impacts, have almost certainly reached Mars, Venus, and possibly the moons of Jupiter. The solar system, it turns out, has been exchanging rocks and potentially life for billions of years. Now scale that up, way up. A star system isn't a closed box. Occasionally, through catastrophic events, a planet colliding with another planet, a close encounter with a passing star. The chaotic early days when solar systems are still forming rocks get ejected with enough velocity to escape their home star's gravity entirely. They become interstellar travellers. Dr. Avi Loeb, the Harvard astrophysicist who spent years studying interstellar objects, estimates that our galaxy contains roughly 10 to 24 such objects at any given time. That's a trillion. Most are small pebbles, boulders, maybe house-sized rocks. But the sheer number means that planet-sized material is constantly drifting between stars. And here's where it gets interesting. Could life survive that journey? Your instinct might be to say no. Space is hostile. The temperature hovers around minus 270 degrees Celsius, just 3 degrees above absolute zero. There's no atmosphere, no liquid water, no energy source. Cosmic radiation, high-energy particles from distant supernovae. From the galaxy's core, from the sun, bombards everything constantly. It's a sterilizing environment, except it's not. Not always. Meet the tardigrade, a microscopic animal about 0.5 millimeter long that looks like a chubby 8-legged bear under a microscope. Scientists have subjected tardigrades to conditions that would kill basically anything else. They've frozen them to near absolute zero. They've heated them to 150 degrees Celsius. They've exposed them to radiation doses 1000 times higher than what would kill a human. The tardigrades went into a state called cryptobiosis, essentially. Suspended animation, and when conditions improved, they woke up and went about their business like nothing happened. In 2007, the European Space Agency launched a mission called Photon M3 that carried tardigrades into low Earth orbit. For 10 days, the organisms were exposed to the vacuum of space and unfiltered solar radiation. When they came back, about 68% survived. Some even remained fertile, producing healthy offspring. Let that sink in for a moment. A tiny creature from Earth survived in space, not in a protective capsule, but exposed to the void. Now, 10 days isn't millions of years, and low Earth orbit isn't the same as interstellar space. But the point is this life, at least certain forms of it, is far more resilient than we assumed. If organisms can survive those extreme conditions even briefly, what about longer timescales? Consider bacteria found in ancient salt deposits, dormant for 250 million years, that scientists revived in the lab. Consider microorganisms discovered in Antarctica's subglacial Lake Whillans, isolated from the surface for millions of years, still metabolizing, still reproducing. Consider the microbes living inside nuclear reactors, feeding on radiation that would kill us instantly. Life finds a way. It's become almost cliched to say that, but the evidence keeps proving it true. So here's the question that keeps astrobiologists awake at night: if rocks can travel between star systems, and if life can survive in conditions we once thought impossible, could an object like 3I/Atlas serve as a lifeboat? Think about the physics. An interstellar object travels for potentially millions of years, but most of that time, it's in deep freeze, metabolism stops, chemical reactions cease. It's not that different from the cryptobiosis that tardigrades use suspended animation on a cosmic scale. But occasionally, maybe once every few million years, that object passes near a star. For a brief window, months, maybe years, it warms up, ice becomes liquid water, organic molecules start moving again, chemistry happens, and if there are organisms inside, dormant in the ice, they might wake up. Dr. Claudius Gross from Goethe University Frankfurt published a paper in 2016 exploring exactly this scenario. His calculations showed that interstellar objects larger than about 300 meters across could maintain liquid water in their interiors for up to several 100,000 years after passing near a star, even as they travelled back into the cold of interstellar space. That's enough time for an entire ecosystem to flourish, produce metabolic byproducts, then go dormant again as temperatures drop. It sounds like science fiction, but the math works, the physics checks out. And if it's possible for Earth-like life, carried on Earth-like rocks, travelling through Earth-like solar systems, what about life that evolves somewhere else entirely, life that might be fundamentally tougher, adapted to conditions we can barely imagine? What if panspermia isn't just a hypothesis, but the primary way life spreads through the galaxy? If that's true, if life can hitchhike on interstellar objects, then 3I/Atlas stops being just an astronomical curiosity. It becomes something far more profound, a potential messenger from another living world, carrying evidence that we are not, and have never been, alone. The spectral signatures Webb detected, the phosphine, the organic compounds, the chemical combinations that look biological, they start to make sense in this context. Not as impossible anomalies, but as exactly what you'd expect from a rock that's hosting dormant life as it travels between stars. But there's a massive gap between theoretically possible and actually happening. For life to survive on 3I/Atlas, the conditions would need to be extraordinarily precise. So let's run the numbers and see if this frozen visitor could actually support living organisms. You're standing on the surface of 3I/Atlas, at least in your imagination. Let's work through what that actually means for survival, not for you in a spacesuit, but for the simplest organisms we know. First, the temperature. Right now, as 3I/Atlas travels through the outer solar system, its surface temperature hovers around minus 200 degrees Celsius. That's cold enough to freeze carbon dioxide into dry ice, cold enough that any water is locked solid as rock. But here's something most people don't realise about temperature in space: it's not uniform. The surface of an object in space gets hit by radiation cosmic rays, the faint light from distant stars, and increasingly, as 3I/Atlas approaches the sun, solar radiation, that surface heats up, even if just slightly, but a few metres below the surface, that's a different story. The ice and rock act as insulation, trap in whatever heat exists from radioactive decay of elements inside the object itself. Every rock contains trace amounts of radioactive isotopes uranium, thorium, potassium, 40. These elements decay slowly over millions of years, releasing heat. It's not much. For an object the size of 3I/Atlas, we're talking maybe 10 to 20 watts of internal heat generation, about the same as a dim light bulb. But in the vacuum of space, where there's no atmosphere to carry heat away, that energy accumulates. Models by researchers at the University of Arizona suggest that objects larger than about 500 meters across could maintain temperatures above minus 50 degrees Celsius in their deep interiors. Even in the freezing void between stars, minus 50 degrees Celsius. Still brutally cold by Earth standards, but here's the thing, we've found bacteria living in permafrost at those temperatures. Psychrophiles, cold-loving microorganisms that remain metabolically active in conditions that would kill most life on Earth. So, temperature surprisingly, it might not be the deal breaker. Now let's talk about water, because life as we know it absolutely requires liquid water. Not ice, not vapour, but liquid. And in space, liquid water shouldn't exist. The pressure is too low. Water either freezes solid or sublimates directly into vapour without ever becoming liquid. Except when it doesn't. Remember that internal heat we mentioned if 3I/Atlas has a core of ice mixed with rock, and if radioactive decay is generating even a tiny amount of heat, you could get pockets of liquid water trapped between layers of ice. Think of it like a subglacial lake on Earth. Lake Vostok in Antarctica sits under nearly 4 kilometers of ice, kept liquid by geothermal heat and the crushing pressure of all that ice above it. Could 3I/Atlas have something similar? Let's run the numbers. At 1.2 kilometers across, the object has enough mass that the centre experiences modest pressure, maybe 10 to 20 atmospheres, about what you'd feel 200 meters underwater on Earth. That's enough pressure to keep water liquid at temperatures slightly below zero, especially if there are salts dissolved in it that lower the freezing point even further. Dr. Dina Prialnik from Tel Aviv University, who specialises in modelling the internal structure of comets, published calculations in 2018 showing that interstellar objects between 1 and 10 kilometres in diameter could maintain liquid water layers for hundreds of thousands of years after passing near a star. The key is insulation. The outer layers freeze solid, creating a protective shell that traps heat inside. But water alone isn't enough. Life needs energy on Earth. Most life ultimately depends on sunlight. Plants and photosynthetic bacteria capture solar energy, and that energy flows through food chains. But in deep space, sunlight is negligible. So where would organisms on 3I/Atlas get their energy? The answer might be chemistry specifically, chemosynthesis. On Earth, we've discovered entire ecosystems living in total darkness, thriving around hydrothermal vents on the ocean floor. These organisms don't use sunlight. Instead, they harvest energy from chemical reactions, typically involving hydrogen sulfide or methane reacting with minerals in the water. If 3I/Atlas has liquid water interacting with rocky material in its interior, similar reactions could occur. Serpentinization, a process where water reacts with certain types of rock to produce hydrogen gas and heat, is particularly interesting because it's been proposed as an energy source for potential life in the subsurface oceans of moons like Enceladus and Europa. The spectral signatures Webb detected those organic compounds. The carbonyl sulfide, they're consistent with exactly these kinds of chemical processes, not proof, but compatible. Then there's radiation, and this is where survival gets really tricky. Space is flooded with high-energy particles, galactic cosmic rays, solar wind, particles accelerated by distant supernovae. This radiation tears through biological molecules, shredding DNA, destroying proteins, killing cells on Earth. We're protected by our atmosphere and magnetic field in interstellar space, and there's no protection, except there is. If you're buried deep enough, ice is an excellent radiation shield. Every metre of ice blocks roughly half of incoming cosmic rays. At depths of just 3 to 5 meters below the surface, radiation levels drop to manageable levels still higher than Earth, but within the tolerance range of extremophile bacteria we've studied. In 2019, researchers at the University of Edinburgh exposed samples of Deinococcus radiodurans, one of the most radiation-resistant organisms known to radiation levels equivalent to interstellar space. The bacteria survived for years when frozen and protected by just a thin layer of simulated regolith. Scale that up to meters of ice, and suddenly the radiation problem becomes solvable. So let's add it all up. Could life survive on 3I/Atlas temperature possible? If organisms are in the insulated interior, liquid water possible, in pressurized pockets kept warm by radioactive decay, energy possible, through chemosynthesis using mineral water reactions, radiation protection possible under several meters of ice. Each of these is a big if. Each requires conditions to align in very specific ways. The odds of all of them being true simultaneously on any random interstellar object are, well, they're low. But here's what keeps the possibility alive. We're not talking about a random object anymore. We're talking about an object that's showing chemical signatures consistent with active processes, that's reflecting light in strange ways, that's behaving oddly as it moves through space. If 3I/Atlas is just a dead rock, why is it acting so strangely? Why the phosphine, a molecule that's difficult to produce and shouldn't persist in space? Why the organic compounds and combinations that look biological? Maybe the answer is that 3I/Atlas isn't dead. Maybe in the frozen darkness beneath its surface. Something is happening. Something metabolic. Something alive. It's still wildly speculative, but it's no longer impossible. And that shift from impossible to merely improbable changes everything about how we need to approach this visitor. The math says survival is possible, but possibility isn't certainty. And we're running out of time to find out for sure, because 3I/Atlas is racing toward a moment that will determine everything we can learn from it. Mark your calendar December 19th, 2024. That's the date when 3I/Atlas reaches Perihelion, its closest approach to the Sun, and it's a moment that astronomers have been planning for since the object was first discovered. But to understand why this date matters so much, you need to understand what happens when something from the frozen depths of space suddenly gets hit with the full force of solar radiation. Picture 3I/Atlas right now. It's roughly 250 million miles from the Sun, about 2.7 times farther out than Earth. At that distance, sunlight is weak only about 14% as intense as what we experience on Earth. The surface temperature is still well below freezing. The object is relatively quiet, outgassing slowly as scattered patches of ice turn directly from solid to vapour. On December 19th, 3I/Atlas will close to within 85 million miles of the Sun just inside Earth's orbit, closer than we are right now. And that changes everything. At perihelion, the solar radiation hitting 3I/Atlas will be roughly 10 times stronger than what it's experiencing now. The surface temperature will spike, potentially reaching minus 50 degrees Celsius or even warmer in spots directly facing the Sun. That might still sound cold to you, but for an object that's spent potentially millions of years near absolute zero, it's a heat wave. What happens when you rapidly heat ice that's been frozen for eons? It doesn't melt gradually, it fractures. Cracks spread through the structure as thermal expansion stresses the material. Pockets of volatile gases, carbon dioxide, carbon monoxide, nitrogen that have been trapped in the ice suddenly find pathways to escape. The outgassing rate can increase by factors of hundreds or even thousands within days. For comet 67P/Churyumov-Gerasimenko, which the European Space Agency's Rosetta mission studied up close in 2014, perihelion triggered dramatic changes. Jets of gas and dust exploded from the surface. The comet's activity increased by over 300%. Entire cliffs collapsed as undermined ice gave way. It was a chaotic, violent transformation of something that had appeared dormant just months before. We're expecting something similar from 3I/Atlas, but unlike 67P, which we'd observed for decades and understood reasonably well. This interstellar visitor is still largely a mystery. We don't know exactly what's beneath that unusually reflective surface. We don't know what happens when those internal pockets, the ones that might contain liquid water, that might harbour chemosynthetic processes, suddenly experience a surge of energy from above. What if the outgassing exposes fresh material from the interior? What if it releases gases that have been trapped since the object formed in another star system? What if those spectral signatures of phosphine and organic compounds become stronger, more obvious, more undeniable? Or what if they disappear entirely, revealed as transient features that had nothing to do with biology? After all, December 19th is our best chance, possibly our only chance to find out. The observation campaigns being coordinated for Perihelion are unprecedented for an interstellar object. James Webb Space Telescope has reserved multiple observation windows in the weeks around Perihelion. The Hubble Space Telescope, despite its age, is being tasked to provide optical imaging at the highest resolution possible. Ground-based observatories from Chile to Hawaii to the Canary Islands are scheduling coordinated observations. The Atacama Large Millimeter Array in Chile, ALMA, arguably the most powerful radio telescope on Earth, is planning to study the molecular composition of gases coming off 3E/8LS. Radio observations can detect molecules that are difficult or impossible to see in optical or infrared light. If there are complex organic compounds in the outgassing material, ALMA will find them. Dr. Martin Cordner from NASA's Goddard Space Flight Center, who's leading part of the ALMA observation campaign, explained the stakes in an October interview. Perihelion represents a unique opportunity. The object will be at its brightest, its most active, and will have weeks of intensive observations from multiple instruments. If there's something unusual about this object, something truly anomalous, this is when we'll see it most clearly. But here's the thing that keeps astronomers on edge. This opportunity is temporary. Brutally temporary. 3I/Atlas is travelling at 180,000 miles per hour relative to the Sun. At Perihelion, it will be moving even faster, whipping around the Sun like a stone on a sling before heading back out into deep space. The window of peak activity when outgassing is strongest, when the object is brightest and easiest to study, will last perhaps 3 to 4 weeks. After that, the object begins its long journey back toward the outer solar system and eventually out into interstellar space. It will fade from view. Within a year, it will be too faint for even our most powerful telescopes to study in detail. Within a decade, it will be gone, swallowed by the darkness between stars, never to return. This isn't like studying Mars or Jupiter, where if you miss your observation window, you can try again next year. This is one shot. One chance to gather data that might answer, or at least meaningfully constrain the question of whether we're looking at the first confirmed instance of life travelling between star systems. The pressure on the observation teams is immense. Telescope time is allocated months in advance. Data reduction pipelines need to be tested and ready. International coordination across time zones, languages, and competing scientific priorities has to work flawlessly. And all of this is happening during the holiday season, when many people would rather be with family than hunched over computer screens watching data streams. But that's science. The universe doesn't schedule its most interesting moments for our convenience. There's another factor that makes December 19th so critical: planetary protection protocols. If there's even a remote possibility that 3I/Atlas harbours living organisms, then we need to know before it gets too close. The object's trajectory will take it inside Earth's orbit. Though not particularly close to our planet, the nearest approach to Earth will be about 140 million miles, well outside any danger zone. But the principle matters. If interstellar objects can carry life, if Panspermia is real and active, then every close approach is a potential exchange event. Earth's gravity could potentially perturb small pieces ejected from 3I/Atlas, and some tiny fraction of that material might eventually intersect our atmosphere. Probably nothing would survive the fiery entry. Probably any organisms would be too different from Earth life to pose a biological threat. Probably were worrying about scenarios so unlikely they are not worth the mental energy. But when you're talking about the possibility of life from another star system, probably isn't quite good enough. The observations are planned, the telescopes are ready, but there's a problem that no amount of planning can solve, even with our most advanced instruments pointed at 3I/Atlas during Perihelion. We might still miss the most important details. Here's a humbling thought. James Webb Space Telescope, the most powerful observatory humanity has ever built, cost $10 billion and took 3 decades to design and construct. Its primary mirror is 6.5 meters across, composed of 18 hexagonal segments coated in gold, engineered to detect light from the first galaxies that formed after the Big Bang. And when it points at 3I/Atlas from 250 million miles away, it's looking at something smaller than a mountain, trying to detect chemical signatures from gases that might be coming off the surface at rates of just a few kilograms per second. Think about what that means. You're trying to identify specific molecules in a thin haze surrounding an object 2 kilometers wide, from a distance roughly equivalent to going from Earth to Mars and back 3 times. It's like trying to identify the ingredients in someone's coffee by sniffing the air from across a football field. The angular resolution, the smallest detail a telescope can distinguish, is a function of the telescope's size and the wavelength of light it's observing. For Webb's infrared instruments, the resolution at the distance of 3I/Atlas is roughly 0.1 arcseconds. That translates to about 120 kilometers at the object's distance. In other words, 3I/Atlas, at just over a kilometre across, appears as barely more than a single point of light. Webb can't see surface features, it can't map the distribution of ice versus rock, it can't identify specific vents or jets or active regions. All it can do is collect the combined light from the entire object and whatever gas surrounds it, then break that light into a spectrum and hope the chemical fingerprints are clear enough to interpret. And that's Webb, our best instrument. Ground-based telescopes, even the massive 10-meter giants in Chile and Hawaii, face additional challenges. Earth's atmosphere, despite what adaptive optics systems can do to compensate for turbulence, still blurs and distorts the light. Water vapor in our atmosphere absorbs certain wavelengths, creating gaps in the spectrum where we simply can't see what's there. When Oumuamua passed through in 2017, we missed almost everything important about it. The object was discovered on October 19th, already on its way out of the solar system. By the time astronomers realised what they were looking at, an interstellar visitor, not an asteroid or comet from our own solar system, it was already fading. They had days, maybe weeks, to gather data before it became too faint to study. The observations we did get raised more questions than answers. The shape was weird, elongated, tumbling oddly. The acceleration was unexplained. And we completely missed the chance to analyse its composition in detail because no one had thought to schedule spectroscopic observations when the object was brightest. Dr. Robert Werrick, the astronomer who first spotted Oumuamua in the Pan-STARRS survey data, later admitted in interviews that the discovery felt like showing up to a party just as the guest of honour was leaving. "We saw something extraordinary," he said, "but we didn't have time to really understand it. That's the nightmare scenario for an astronomer. You discover something amazing, and it's gone before you can study it properly." The scientific community learned from that mistake. When Borisov was discovered in August 2019, still months away from Perihelion, the response was immediate and coordinated. Telescopes around the world were tasked to observe it. Spectroscopic campaigns were organised. Data sharing agreements were put in place. And we learned vastly more about Borisov than we ever did about Oumuamua, simply because we had time to prepare. 3I/Atlas benefits from that same advanced warning. We've known about it since April, giving us months to plan. But here's the uncomfortable truth. Even with all that preparation, we're still fundamentally limited by the physics of observation. Consider the phosphine detection. The spectral feature Webb identified is real. The instrument saw absorption at 2.85 microns, right where phosphine should appear. But that feature is faint. The signal-to-noise ratio, a measure of how clear the detection is versus random fluctuations in the data, is only about 4.5. In most fields of science, that would be considered a solid detection. In astronomy, where you're pushing instruments to their absolute limits, it's enough to be interesting but not enough to be conclusive. Other teams have tried to confirm the phosphine detection using ground-based telescopes. So far, results are mixed. Some observations show hints of the same feature, others don't see it at all. That could mean the phosphine emission is variable, it comes and goes as different parts of 3I/Atlas rotate into sunlight. Or it could mean the feature is at the very edge of detectability, appearing in some datasets but drowned out by noise in others. This is the frustrating reality of cutting-edge science. You're not working with clear, obvious signals. You're working with faint whispers buried in noise, trying to extract meaning from data that's right at the limit of what your instruments can measure. And there's another problem that nobody likes to talk about: timing. Telescopes like Webb and Hubble are in high demand. Thousands of scientists around the world want to use them for their research. Time on these instruments is allocated through a competitive proposal process months in advance. You write a proposal, justify why your observation is important, and hope the review committee agrees. For 3I/Atlas, astronomers requested time based on predictions of when the object would be brightest, when outgassing would be strongest, when spectroscopic observations would have the best chance of success. But those predictions are based on models of how interstellar objects behave. Models built from exactly 2 previous examples, both of which were weird in their own ways. What if 3I/Atlas doesn't follow the predicted pattern? What if peak outgassing happens 3 days before the scheduled observations, or 2 days after? What if the most interesting chemical signatures only appear for a brief window hours, not days when the right combination of surface features rotates into direct sunlight? We could miss it. Through no fault of the instruments or the astronomers, simply because the universe doesn't care about our observation schedules. There's a reason why the teams planning the December observations are stressed. They're not just worried about technical failures or data processing errors, they're worried about the fundamental possibility that even if 3I/Atlas is carrying something extraordinary, even if there are biosignatures there, clear and obvious, we might be looking in the wrong place at the wrong time with instruments that aren't quite good enough to see what we need to see. It's like trying to catch lightning in a bottle, except the lightning is 250 million miles away. The bottle is a multi-billion-dollar telescope that you can only use for a few hours, and you have one chance to get it right. The limitations are real, the challenges are daunting, and the stakes couldn't be higher. But before we get too caught up in the possibility of finding life, there's another side to this story: the scientists who are pushing back, offering alternative explanations that don't require anything as extraordinary as biology. There's a principle in science that you've probably heard before: Occam's razor. When you're faced with multiple explanations for the same observation, the simplest one, the one that requires the fewest assumptions, is usually correct. And right now, a significant portion of the scientific community is wielding that razor with considerable force against the idea that 3I/Atlas might be carrying life. Doctor Jane Greaves knows this tension intimately. She's the astronomer who, in 2020, announced the detection of phosphine in Venus's atmosphere, a claim that sparked immediate excitement about possible life in the clouds of our neighbouring planet. The media ran wild with headlines about aliens on Venus, but within weeks, other scientists began publishing critiques. The spectral feature might not be phosphine at all. They argued it could be sulfur dioxide in an unusual configuration, or an instrumental artifact, or contamination in the data processing. The debate continues to this day, still unresolved. In a recent seminar about 3I/Atlas, Greaves was cautiously optimistic but clear-eyed about the challenges. We need to be very careful not to repeat the Venus situation. Before we claim biosignatures, we need to exhaust every possible non-biological explanation. And trust me, there are many. So let's walk through those explanations. Let's be the skeptics for a moment and see how well the non-biological alternatives actually hold up. the phosphine detection that 2.85 micron spectral feature could potentially be explained by photochemistry. When ultraviolet light from the sun hits molecules containing phosphorus, it can drive unusual chemical reactions that might produce small amounts of phosphine without any biological involvement. In 2021, researchers at Washington University modelled phosphine production on airless bodies and found that under very specific conditions, particular mineral compositions, specific radiation environments, you could get trace phosphine formation. But there's a catch. The models require phosphorus-bearing minerals to be exposed on the surface and continuously replenished as the phosphine breaks down in sunlight, and they predict phosphine abundances roughly 100 times lower than what Webb appears to be detecting from 3I/Atlas. Could the models be wrong? Absolutely. Could there be some process we haven't considered that ramps up phosphine production? Sure. But that's the thing about non-biological explanations. They have to work within the bounds of known chemistry and physics. You can't just say maybe there's some weird process without showing that the process is actually possible. The organic compounds the carbon-hydrogen signatures. The carbonyl sulfide, those are easier to explain without invoking biology. We know that space is surprisingly good at making complex organic molecules. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, most of which don't even exist in terrestrial biology. These molecules formed through purely chemical processes in the early solar system. No life required. In fact, the field of astrochemistry has exploded in recent decades precisely because we keep finding organic molecules in places we didn't expect. Interstellar clouds, protoplanetary disks, comet surfaces, even in the atmosphere of Saturn's moon Titan, where methane and nitrogen react in the upper atmosphere to create a brownish haze full of complex hydrocarbons. Dr. Scott Sanford from NASA Ames Research Center, who studies organic chemistry in space, points out that the mere presence of organic molecules tells us almost nothing about biology. Carbon is the fourth most abundant element in the universe. It bonds readily with hydrogen, oxygen, nitrogen. All the ingredients are there in space. Chemistry happens. Complex molecules form. That's not controversial. What would be controversial is if those molecules showed specific patterns, specific chirality, specific ratios, specific molecular structures that we only see in biological systems on Earth. And so far, the spectra from 3I/Atlas don't show that level of detail. The resolution isn't good enough. We're seeing broad features that tell us organic compounds are present, but not which specific compounds or in what arrangements. Then there's the high albedo, that unusually reflective surface. Dr. Dennis Bodowitz from Auburn University has proposed that this could be explained by a fresh layer of ice brought to the surface by recent outgassing. If 3I/Atlas passed near a star sometime in the past few thousand years, it could have experienced a surge of activity that resurfaced the object, covering old, darkened material with bright, pristine ice, the stable rotation. That's trickier to explain, but not impossible. If 3I/Atlas experienced a collision in the past, say, with another object in its home system before it was ejected, the impact could have imparted angular momentum that resulted in a stable spin. It's improbable. But improbable things happen all the time, in a galaxy with hundreds of billions of stars. The velocity anomaly could be outgassing that we're not detecting effectively. Maybe the jets are on the side facing away from us. Maybe they're composed of molecules that don't show up well in our observations. Maybe the outgassing is pulsed active for a few hours, then dormant, then active again, and we're missing most of it. Each anomaly, taken individually, has at least one plausible non-biological explanation. And if you're a scientist trained to be skeptical, trained to demand extraordinary evidence before accepting extraordinary claims, you look at this collection of anomalies and you think, this is interesting, but it's not conclusive. We need more data. And you'd be absolutely right to think that the problem, and this is what keeps the debate alive, is that none of these alternative explanations feel entirely satisfying. Each one requires its own set of special conditions, its own coincidences. When you add them all up, when you need 5 or 6 different unusual processes to explain 5 or 6 different anomalies, you start to wonder if maybe, just maybe, there's a single explanation that ties everything together more elegantly. This is where Occam's razor gets tricky, which is simpler, 6 separate, unusual but possible processes, each explaining one piece of the puzzle or one extraordinary process, life, that explains multiple pieces simultaneously. Carl Sagan famously said, "Extraordinary claims require extraordinary evidence." And he was right. The burden of proof is on those claiming that 3I/Atlas harbours life. Skepticism is not just appropriate, it's essential. It's how science protects itself from wishful thinking, from jumping to conclusions, from letting excitement override rigour. But Sagan also said something else that's worth remembering. Absence of evidence is not evidence of absence. Just because we haven't proven that life can travel between stars doesn't mean it can't happen. Just because we've never detected biosignatures on an interstellar object before doesn't mean 3I/Atlas isn't the first. The debate isn't settled. It won't be settled until we have better data, clearer observations, more time to analyse what we're seeing. And that's okay. That's how science works. Slowly, carefully, with arguments and counter-arguments, papers and rebuttals, conferences where researchers present competing models and pick apart each other's assumptions. While scientists argue about what 3I/Atlas is, there's another conversation happening, one that's less about the data and more about what we should do with it. Because if there's even a chance that this object carries life, the implications stretch far beyond academic debate. On November 8th, a closed-door meeting took place at the United Nations Office for Outer Space Affairs in Vienna. The attendees included representatives from NASA, ESA, the Japan Aerospace Exploration Agency, Roscosmos, and space agencies from another dozen countries. The topic wasn't officially disclosed, but sources familiar with the meeting say it centred on a single question: what do we do if 3I/Atlas confirms our suspicions? Because here's the thing, we don't actually have a plan for this. The Outer Space Treaty of 1967, which forms the backbone of international space law, covers a lot of ground. It prohibits nuclear weapons in orbit. It establishes that no nation can claim sovereignty over celestial bodies. It requires that space exploration be conducted for the benefit of all countries. But nowhere in that treaty, or in any of the subsequent agreements, protocols, and frameworks developed over the past 50 years, does it address what humanity should do when we encounter potential life from another star system passing through our cosmic neighbourhood. There's a framework called Planetary Protection, developed by the Committee on Space Research, COSPAR for short. It's designed to prevent biological contamination in two directions, protecting other worlds from Earth life, and protecting Earth from potential extraterrestrial organisms. NASA and other space agencies follow these protocols religiously. When Curiosity rover was sent to Mars, it was assembled in clean rooms and sterilised to ensure we didn't accidentally contaminate Mars with terrestrial bacteria. But those protocols were written with one assumption: that we control the encounter. We choose when and how to interact with potentially life-bearing environments. We can sterilise our spacecraft. We can select landing sites carefully. We can contain samples and quarantine them. 3I/Atlas doesn't care about our protocols, is not asking permission to pass through, and if it's shedding material dust, gas, possibly even small fragments knocked loose by outgassing or micrometeorite impacts, then that material is already mixing with the solar system's natural dust cloud. Some of it will eventually spiral into the inner solar system. Some tiny fraction might even reach Earth's atmosphere. Should we be concerned? The honest answer is probably not. But we don't actually know. Dr. Catherine Conley, who served as NASA's Planetary Protection Officer from 2006 to 2017, has written extensively about this scenario. In a 2018 paper exploring the implications of interstellar visitors, she noted, "Our planetary protection protocols assume we can control the interaction. With interstellar objects, we can't. They arrive unannounced, pass through rapidly, and leave. If they're carrying biological material, we're exposed whether we like it or not. The risk of actual contamination is probably minuscule. Any organisms on 3I/Atlas would have evolved in a completely different environment, around a different star, with different chemistry. The chances that such organisms could survive in Earth's biosphere, let alone compete with 3.8 billion years of terrestrial evolution, are extraordinarily low. But extraordinarily low isn't zero. And when you're talking about potential biosphere contamination, even tiny risks warrant serious consideration. Then there's the flip side. What if we want to study 3I/Atlas more closely? Multiple groups have quietly begun feasibility studies for rapid response missions. The concept is straightforward if the December observations confirm that something truly anomalous is happening. Could we launch a spacecraft to intercept 3I/Atlas before it leaves the solar system? The challenges are immense. 3I/Atlas is moving at 180,000 miles per hour. Catching up to it would require a spacecraft with extraordinary velocity far beyond what our current propulsion systems can easily achieve. For comparison, New Horizons, the fastest spacecraft ever launched, reached Pluto travelling at about 36,000 miles per hour relative to the Sun. To reach 3I/Atlas, you'd need to go 5 times faster, but it's not impossible. In October, a team from the Johns Hopkins Applied Physics Laboratory, the same group that built New Horizons, published preliminary calculations showing that a spacecraft using a Jupiter gravity assist combined with advanced ion propulsion could potentially intercept 3I/Atlas sometime around 2027 or 2028 while it's still within the outer solar system. The cost would be staggering, probably $2 to $3 billion for a rushed mission with existing technology. The timeline would be punishing design. Build and launch within 18 months to catch the right trajectory window. And the scientific return would be uncertain. By the time the spacecraft reaches 3I/Atlas, the object will be far from the Sun, cold and dormant again, making observations more difficult. But imagine the payoff if it works. Imagine a spacecraft flying past 3I/Atlas at close range, cameras capturing surface details at meter-scale resolution. Imagine spectrometers sampling the gas directly from active vents. Imagine mass spectrometers identifying the exact molecular composition of organic compounds. Imagine confirming, once and for all, whether those biosignatures are real. That's the scientific case. But there's another conversation happening in parallel, one that's less about discovery and more about meaning. If 3I/Atlas carries life, it fundamentally changes our place in the universe. We've spent centuries wondering if we're alone, searching the skies for radio signals, planning missions to Mars and Europa and Enceladus in hopes of finding even simple microbes. The discovery of life beyond Earth, any life, anywhere, would be one of the most profound moments in human history. But this wouldn't be life we discovered through our own exploration. This would be life that came to us. Life that, in a sense, visited. And that changes the psychological and philosophical impact in ways that are hard to predict. Dr. Douglas Verkoch, president of METI International and a researcher who studies humanity's potential reactions to contact with extraterrestrial life, conducted surveys in 2016 asking people how they would feel about various discovery scenarios. Finding microbial life on Mars. Most people reacted with curiosity and excitement. Detecting an intelligent signal from a distant star, more mixed reactions: excitement, anxiety, wonder, fear in roughly equal measure. But finding life travelling through space, life that might have originated in a completely different stellar environment, life that's been journeying through the galaxy for who knows how long, that scenario wasn't even on the survey. We don't have a framework for how people might react, because we've never seriously contemplated it before. The Vienna meeting in November didn't reach any formal conclusions. How could it? The science is still uncertain, the observations aren't complete. We're in that uncomfortable space where we know enough to be concerned, but not enough to be certain. What the meeting did accomplish was this: it got the relevant organisations talking. It established communication channels. It began the process of thinking through scenarios, considering options, preparing responses not because anyone believes we're facing an imminent crisis, but because that's what responsible institutions do when confronted with possibilities they've never had to consider before. All the meetings, all the protocols, all the feasibility studies, they're happening in conference rooms and research labs, places most people never see. But 3i/Atlas isn't just a challenge for scientists and policymakers, it's something deeper, something that touches on questions humans have asked since we first looked up at the night sky and wondered what else might be out there. Step outside tonight, look up at the stars, those pinpoints of light scattered across the darkness. Each one is a sun, many with their own planets, their own systems, their own histories stretching back billions of years. Now consider this somewhere up there. Around one of those distant stars, 3i/Atlas began its journey. It formed in a protoplanetary disk, possibly accreted from the same cloud of gas and dust that created planets we'll never see. Something happened, a gravitational encounter, a collision, a close pass by another star that ejected it from its home, sending it drifting through the void. For millions of years, it travelled alone through the darkness between stars, a tiny island of matter in an ocean of nothing. No sunlight warmed it, no planets influenced its path. Just the slow, patient drift through space at speeds that make our fastest rockets look stationary. And then, by chance or fate or simple probability, playing out across billions of such objects in the galaxy, its trajectory intersected with ours. It fell into our solar system, past Neptune, past Uranus, past Saturn and Jupiter, closing now on the Sun that has warmed Earth for 4.5 billion years. If 3i/Atlas carries life, if those spectral signatures hold up, if the December observations confirm what we suspect, then that object represents a connection between two worlds that may never know each other exists. Life that evolved under a different sun, shaped by different chemistry, different physics, different evolutionary pressures, has travelled across the light years and arrived here. Think about what that means for a moment. Really think about it. For most of human history, we believed Earth was the centre of everything. The sun, moon, planets, and stars all revolved around us. Then Copernicus showed that Earth orbits the sun, not the other way around. Then we discovered the sun is just one star among hundreds of billions in our galaxy. Then we found that our galaxy is one among hundreds of billions of galaxies. Each revelation pushed us further from the centre, made us smaller, made the universe larger and stranger than we imagined. But through all of that, one question remained. Are we alone? Is life something unique to Earth? A cosmic fluke that happened once in 13.8 billion years of universal history, or is life common, emerging wherever conditions allow, scattered throughout the cosmos? We've sent spacecraft to Mars searching for fossils of ancient microbes. We've detected thousands of exoplanets, calculating which ones might have liquid water and atmospheres that could support life. We've pointed radio telescopes at promising star systems, listening for signals that would indicate technological civilizations. But we've never not once found definitive evidence that life exists anywhere beyond Earth, until, possibly, now, if 3i/Atlas confirms what we suspect. It doesn't just answer the question of whether we're alone, it answers it in a way that's simultaneously more wonderful and more unsettling than any scenario we've seriously contemplated. Because this isn't life confined to its planet of origin, waiting for us to discover it. This is life that travels, life that spreads, life that perhaps is right now distributed throughout the galaxy on millions of similar objects, drifting between stars, seeding worlds, creating a vast network of biological connection that spans distances we can barely comprehend. The implications cascade outward like ripples in a pond. If panspermia is real, if life can survive these journeys, then the origin of life on Earth itself becomes questionable. Did life start here, through some process of chemistry becoming biology in Earth's ancient oceans? Or did it arrive here, carried on a rock from Mars, or from somewhere even more distant? Some of the oldest fossils on Earth date back 3.5 billion years, appearing relatively soon after the planet cooled enough to support liquid water, that's always seemed suspiciously fast. If life emerged from non-living chemistry, you'd expect it to take longer many more millions of years of trial and error before the right combination of molecules came together. But if life arrived here, already formed, already adapted to survival in extreme conditions, already capable of metabolism and reproduction, then the timeline makes more sense. And if life arrived here, then Earth isn't the origin point. We're a branch, not the trunk, somewhere out there, maybe around the star that 3I/Atlas came from. Maybe somewhere even more distant is the world where our ancestors first evolved. A world we've never seen and may never find. That's the scientific implication. But there's a human side too. One that's harder to quantify, but no less profound. We've spent the past century coming to terms with our cosmic insignificance, the realization that we're not central, not special, not the purpose of the universe. That's been a difficult, sometimes painful adjustment. Religions, philosophies, entire worldviews have had to adapt to the knowledge that Earth is a tiny planet orbiting an ordinary star in an unremarkable galaxy. But there's a flip side to that insignificance isolation. If we're not special, if we're just the product of ordinary physics and chemistry, then at least we're here. At least we exist. At least in this one corner of the universe, matter organized itself into something that can think and feel and wonder about its place in the cosmos. The discovery of life beyond Earth, especially life that travels between stars, breaks that isolation. We're not alone. We never were. The universe isn't a lifeless void with one tiny exception called Earth. It's a place where life happens, where it persists, where it finds ways to spread and survive and continue. For some people, that will be profoundly comforting, the end of cosmic loneliness, the knowledge that life is resilient and widespread. For others, it will be unsettling, a reminder that we're even less special than we thought, that life doesn't need Earth, that we're part of something much larger that existed long before us and will continue long after. Both reactions are valid, both are natural, because this isn't just science anymore. It's philosophy, it's meaning, it's about how we understand ourselves in relation to the universe. On December 19th, 3I/Atlas will reach Perihelion. Telescopes around the world will be watching. Data will stream in. Scientists will analyse spectra, debate interpretations, write papers, argue at conferences. And somewhere in all of that, we might get our answer. Maybe the biosignatures will disappear, revealed as artifacts or misinterpretations. Maybe the alternative explanations will prove correct, and 3I/Atlas will become just another interstellar rock with some unusual chemistry. Or maybe, just maybe, we'll confirm what the data is hinting at. And in that moment, everything changes. Not immediately, not dramatically. The sun will still rise, life will continue, but underneath it all, we'll know something we didn't know before. We'll know we're part of something bigger. We'll know life doesn't stop at planetary boundaries. We'll know that when we look up at the night sky, we're not looking at a sterile void, but at a cosmos alive with possibility. 3I/Atlas will leave our solar system in early 2025, fading back into the darkness between stars. Its visit here is temporary, a brief encounter measured in months. But the questions it brought with it, those will stay with us forever.